Okie doke. It's time for my last lot of videos. I think it's the last lot anyway. And it's turn it around so Janina can see the time. It's about substitution between alternative resource inputs, and then with the understanding of this substitution in mind, we're then going to look at pollution. So remember then, it's about, we've got household, firm, resource sector, and now we've got like two resource sectors. And often when I'm sort of waving my hands around, I talk about models with labour going either to the final good firms or to the extraction sectors, and we've had one or two models like that too, but there's also a modelling alternative where the final product, the widgets, can either be sent to the households for consumption or to the mines for extraction, so to speak. And I think that's what's going on in this model we're going to go through, if I remember rightly. And then these goods go into the black box and deliver the resource input R. Labour, production, consumption. X is the inputs of widgets into these sectors. Do we call it X? No, we don't. Whatever it is, Y minus C. Okay, so that's the kind of picture we've got. Right. And we're going to go straight to the bottom of this slide and say that we've got Cobb-Douglas, so Y is ALL to the 1 minus alpha, R to the alpha. And R is made up of this productivity term, which is widgets per ton times gamma C AC to the epsilon plus gamma D AD to the epsilon, all to the 1 over epsilon. Okie doke. So if R has unit, if we think of R as electricity, for instance, that might have units like megawatts, megawatt hours per day or something, or just megawatts, I guess. Let's say megawatt hours per day. Then this is like, oh, these shouldn't be A's, should they? X's. This is like tons per day. This is some factor. Yeah, this is tons of coal per day. And this could be like joules per ton or something. So then this would be joules per day of coal from the coal, and this would be joules per day from something else. Up to the epsilon is joules per day, to the epsilon, to the 1 over epsilon. So this is like joules per day, and then this would be megawatt hours per joule. I don't know, something like that. Okay, and consumption, C, is Y minus, Y is divided between consumption and the inputs into these sectors, which is yeah, okay. And what are the inputs? How much inputs here? Well, if the price of the output from from sector C is WC, and the price of the input is 1, because that's widgets, the price of which is 1, then the quantity of the input must be WC XC, where XC is the quantity of output. Okay. So if WC is big, that means that you need a lot of the input to get a certain amount of output. And of course, you could work this out by setting up a profit maximization problem for this guy, sort of using the inputs to get the outputs. So if we let's do it quickly, okay, because I don't want you thinking this is something weird. Okay, it's a good little exercise. So let's just do it. Let's call the inputs into this sector, let's call them ZC. Inputs ZC. Cost of those inputs ZC, because each unit of input costs 1. Output XC. Cost of output. Well, the total cost is also ZC, isn't it? So the unit cost per unit of production is ZC over XC. And since we're assuming perfect markets, the price charged for this input, for this XC, will be equal to unit cost. Okay, and we call that price WC. So we've got ZC over XC equals WC, or ZC is WC XC. So that's the amount of inputs into this sector, WC XC, and ZD would be WD XD. Okay. So therefore, C is Y minus WC XC plus WD XD. Okie doke. Next slide. So we want to go to the electricity producer and look at their problem. So we kind of looked at the problem here and we just got this simple result with these inputs and the output. We've given the prices. But now we want to look at the profit maximization problem of the electricity producer in the black box. The revenue of that producer is WR, the price of electricity, times the quantity of electricity, R. And we need to bear in mind that this is the expression for R, right? Profit is the revenue minus costs, which is WCXC plus WDXD. Okay, so next step, we want to solve this problem for how much C and D is this final good producer going to buy. So we want to take first order conditions in XC and XD. So remember, we've got perfect markets, so the representative electricity producer is a price taker and decides on the quantities. Yeah, we need to have this kind of thing totally clear. Yeah. So we're going to take first order conditions in XC and XD. And then we get, so d pi dxc is 0. So d this by dxc should be equal to d this by dxc. Yeah? So we can write WC should be should be equal to d this by dxt, which is WRA and then this by dxt. Okay, which is, do the outside, 1 over epsilon, square bracket to the 1 over epsilon minus 1, which is 1 minus epsilon over epsilon, and then we go inside and we have epsilon, so that cancels. Do it like an economist, gamma c xc to the epsilon over xc. Okay? And then we just bring that xc up. So we have that. Then we do the same thing for d, and we have wd xd is wra, that okay. And then we divide one by the other, and we get okay, we're not quite there yet. We divide one by the other and we get WC XC over WD XD is gamma C XC over gamma D XD to the epsilon. We don't really like this because this is what we want to know, but the XC and XD are unknown as well. So we've got unknowns on both sides. That's a mess. We're thinking that the prices of these are known because it's equal to the extraction costs, which we know. So WC and XC are known. Sorry, WC and WD are known, but XC and XD are unknown. So how do we deal with this? We multiply both sides by WC XC over WD XD to the minus epsilon. And then we get WC XC over WD XD to the 1 minus epsilon equals. So we multiply by WC XC to the minus epsilon. So that XC, epsilon XC minus epsilon, that's going to go out, and we end up with a WC on the bottom line, kind of. We end up with gamma C over WC. And so the symmetric argument gives gamma D over WD all to the epsilon. Okay. If you can't see that, just do it for yourself on paper using a couple more lines, a couple more steps. And now we can just raise both sides to the 1 over 1 minus epsilon, and we end up with, take that away, epsilon over 1 minus epsilon. And that's our result. Okay, and the inputs are good substitutes, as we talked about in the lecture. Epsilon is greater than 0, which means that a cheap input takes a big factor share. WC small, WCXC big. Which means that if an input gets cheaper over time, its factor share will rise. Okay, there's a bunch more stuff which I wasn't ready for. Let me have a look at that. Okay, I had to think for a while there, because I did this step to get rid of the x's from the right hand side and get w's instead. I did it kind of at the end, but what I should have done was do it earlier. If you look at the slide, I'd do the same kind of step. It's basically exactly the same process, but I do it directly on these equations separately. Where this square bracket to the 1 minus epsilon over epsilon is the same as r over a, to the 1 minus epsilon. Because r over a is square bracket to the 1 over epsilon, isn't it? So r over a to the 1 minus epsilon is square bracket to the 1 minus epsilon over epsilon. So if I'd done that step earlier on these two separately, then I have these two equations in WCXC in terms of WR and WC and R over A, and WDXD in terms of WR, R over A, and WD. Okay. And then we're in a position to work out WR. I think I'll rub off like that. So if you look at the equations on the slide, what is WR? The price of this output. Again, it's very simple here. Price is going to be equal to unit cost. And what's unit cost? It is the sum of the inputs costs over quantity. But here we've got equations for WCXC and WDXD. When we put those together, we get WR to the 1 over 1 minus epsilon times R over A times gamma C over WC to the epsilon over 1 minus epsilon plus gamma D over WD to the epsilon over 1 minus epsilon. All, no, that's it, yeah. And then that's the top line, and then we divide by R. So we end up with WR to the 1 over 1 minus epsilon divided by A times that. Okie doke. Another thing. Wow. It's quite tricky, this. So we've got WR equals WR to the 1 over 1 minus epsilon, blah, blah, blah. So if we take this over, we end up with WR to the 1 minus epsilon over 1 minus epsilon minus 1. So that's minus epsilon over 1 minus epsilon. And like that. Then we got that. Okay. And then we can take the A inside here and say 1 over A plus 1 over A. And like that. And then we can raise to the power of minus 1 minus epsilon over epsilon to get WR. And then we're going to need to okay, no, I should never have taken this A inside here. It's just 1 over A. Okay. So we've got a minus sign here. So if we raise to the power of minus 1, that becomes plus. Turn that over and turn this over. Or if you like, put a line there. A divided by that one. Now raised to the 1 minus epsilon over epsilon, you have A to the 1 minus epsilon over epsilon times that square bracket to the 1 minus epsilon over epsilon. And I'm pretty sure that's right, and it's wrong in the slide. Okay. So we've got that equation for WR, and I'm going to have another think. Okay. And we know that WR equals alpha Y from the Cobb-Douglas production function. So if we stick the expression for Y in the Cobb-Douglas, we end up with WR is alpha ALL over R to the 1 minus alpha, isn't it? And then we've got two different expressions for WR. We can eliminate them, and we end up with an expression for R, the quantity of electricity. Okay, so we worked out the price of electricity. It was quite a mess. We worked out another expression, and it was linked to the prices of the inputs and productivity. Then we worked out another expression for the price of electricity in terms of productivity, the labor, and the quantity of electricity. And then we eliminate the price, and then we have an expression for the quantity. And we end up with ALL times a bunch of stuff. So if the prices are constant, the quantity tracks the growth rate, which is, of course, exactly what we'd expect. Okay, that was a lot of work to get a pretty straightforward result, right? That if the prices of these two are constant, then the price of the electricity will also be constant, and therefore the quantity of electricity will track the growth rate. So the math, a lot of fiddly math, but super straightforward result. Okay, let's stop there.